All right, let's get started. All right, so last time we did searching and sorting graphs. Today we're doing shortest path. Again, I think you've seen this in part before. Okay, so if we get through it fast, there's some problems at the end. Okay, so let's look at this graph. Um, what's the fastest way to get from S to T? I always forget to put this arrow here. Let's put it like that. Okay. All right. So you're trying to minimize the number of edges to get from S to T. Yeah. Oh yeah, that's the algorithm. But what's the actual answer for this? You're not even gonna try? 6? 7? 6 or 7? You're young, you should be able to. 7? Okay. Alright, who got 7? Anyone get 6? But you didn't get, you just, okay. Alright. Okay, so I'm just gonna, you just tell me like which direction to go. Okay, we'll do it in, teal. Alright, should I go up or down? Like, up? Up or down? Uh, up or right? Okay, I guess down to the right? Okay, and then up to the right or down to the right? I don't know. You tell me. Up or down? Down, and then to the right. One, two, three, four, five, six, 7. Okay. But can you get 6? But it's like a little hard to like rule it out staring at it, right? So we also want to come up with a systematic way not only to figure out how to get there, but feel very confident in the answer. Okay, so let me quickly do some definitions. So in addition to unweighted setting, we'll also do at weighted settings with edge lengths. And it won't really come up today, but they could be negative numbers too. Today we'll focus on non-negative numbers or just the unweighted case. So, what's there to say? I guess this would be a path from S to T, and what do these numbers add up to? 11? Is that correct? All right, so I guess this is a walk of length 11. Okay, so we're going to define the distance to be the infimum. The distance from S to T will be the infimum length of all walks from S to T, right? So that's really saying minimum, but with special exceptions for when, if there's no path, we just call that infinity. And if the length can be arbitrarily negative, right, there could be negative cycles, that'll be a topic next time, then that's negative infinity. Okay, infimum is just a fancy way to take care of these edge cases. Okay, good. And the one thing that distances obey is something like a triangle inequality. I think we went over this sort of implicitly when we talked about edit distance. I'm trying to get the fastest way from A to B, and I'm looking at some point in the middle, C, right? A to C plus C to B is at least going from A to B, since you are going from A to B. Okay, good. Nothing special. All right. So, okay, so systematically from first principles, right? How will we try to figure out the shortest path from S to T, right? Or let me put it another way. What's like the easiest choice of T if you're trying to find the shortest path from S to T in this graph, or the shortest length? Huh? Or S itself? The easiest choice of T. Yeah, so for example, this one here, you know is distance 0, right? And then what would be like the second easiest? Yeah, the vertices at distance 1, right? Once you figured out distance 0, it's relatively easy to figure out distance 1. Once you figure out distance 1, it's relatively easy to figure out distance 2, right? Although I always mess this up. Right, there's distance 2. Oh, see? I think that's distance 2. Okay. Once you figure out everything at distance 2, then we could try to figure out everything at distance 3, which, if we do this correctly, I think that's correct. Okay. Now, no, it's really hard to figure out distance 3 without distance 2. Like, you'd have to think really hard even with just like 5 nodes to make sure you don't miss something, right? Okay. Once you figure out distance 3, you can figure out distance 4. Still a little bit hard. Is that correct? Did I miss one? I think that's distance 4. Now that we have distance 4, try to figure out distance 5. Yeah, that's distance 5. Once we have distance 5, we can figure out distance 6, and this one's, I think, going to be a little unusual. We did? Yeah, but can we actually get there? This one? This one? This one is 5? How do we get there? This one is 5? Where is the edge from a 4? Okay, so once you figure out 5, you could try to figure out 6. I think it does something weird like that. And then once you figure out 6, you can figure out 7. And I guess we have one more for 8. Did I leave something out? Uh, this one? Oh, this should be 7 actually. Okay, alright. Okay. Okay, but if you do it this way, and you are willing to spill the ink, then you could feel very good that you found the right distance is 7, right? So here we not only figured out the distance is 7, but like we really know it's 7. It's not 6. It's not 8. I guess you already knew it's not 8, but okay, good. So, all right, so that's our algorithm, right? That's breadth first search. You just build out these layers one at a time. What's there to say about it? Not much. Just figure out distance 0, distance 1, distance 2. You go through every vertex once. It's going to take you linear time. Good. Okay, how do we prove this is correct? Okay, so, okay, I think there's some notation I want to be a little bit sensitive to. So, the way I've written the algorithm, I've created some array called distance that I'm gradually filling out. Okay, so distance refers to, in particular, the values assigned by our algorithm. And in this proof, dsv will refer to the true distance. Okay, and distance of v on the right will refer to this label from the algorithm. Okay, so what I really want to argue is that all the distances, dsv is always equal to that distance label of v, right? I want to say I labeled everything correctly. And how am I going to do this? Well, the way it's set up is we're going to try to do this by, well, maybe I should ask. Well, I guess we're going to try to do all the layers separately, right? It's saying for every value k, the vertices at true distance k from S are exactly the vertices that are labeled k, right? The left set is the things at actual distance k. The right set is the things labeled k. All right. Who wants to just suggest how to prove this in a word or type of proof? Yeah. All right, we can prove this by induction on k, right? Just like we did the algorithm together. So what's the base case? Yeah. Well, it's in terms of k, so that's 0, right? 0, that's only our starting point, because otherwise you need an edge. That's pretty easy. So in the general case, right? So in the general case, ooh, this is coming out weird. That spoiled. Okay, didn't come out as nice as I would like. Oh, did I erase this? Okay. Sorry, guys. Okay, so, all right, this didn't go as well as I'd hoped. That's okay. So at the top, we've just written sort of the definition of BK based on our algorithm, right? So it's these vertices that we haven't marked already, but they have an edge from the k minus 1th layer. Okay, and they're just writing it out in some compact notation. And AK, which is the true distance, actually has a very similar definition, right? It can't have distance less than k, so it can't be in any of the A0s through AK minus 1, but it needs to have an edge from the AK minus 1 set. Okay, so those are just two, what is BK, what is AK, and BK is defined in terms of B1, B2, B3. AK is defined by B, A1, A2, A3, and by induction, A1 is B1, A2 is B2, and then we say, oh, it's the same. Okay, good, so that's it. Nothing fancy. Oh, okay, there it is. All right, so, good. I only briefly want to mention, because this is often how it's introduced, you could also implement breadth first search with a queue, right? As you label a vertex, you insert into a queue and you pull out the next vertex, you start exploring its neighbors. Yeah, and as far as I can tell, the only way to prove this is correct is by showing it's simulating the obvious layer-wise search, that it's processing one layer at a time before the next one. Okay. All right, good. So much for that. I assume you've all seen that before to some extent, but it's just a warm up. All right, let's go to positive weights. Yeah, okay, so in this graph, what's the distance from S to T? Those purple numbers denote edge lengths. 12. Okay. Anyone beat 12? 15? 15? Okay. Anyone beat 15? All right. How did you get 15? Just to show me the way. So, start at S up, down. All right, that's 15. 5, 13. Yeah, I don't know how to do better. Okay. All right. So at least you guys get the idea, right? Okay. So you understand the problem. Now, suppose we're going to try to develop an algorithm you probably know well from first principles. But suppose, at some level we know how to do unweighted edges, right? And suppose you have a case where everything's an integer like this. What's one way to sort of reduce our integer weighted setting to unweighted? Yeah, so I could split these edges. So this first edge was length 4. I can put 3 vertices in between. Yeah, and think of that as 4 unweighted edges. 2 vertices down here, 2 vertices here, right? You can split the edges, and turn this weighted graph into an unweighted graph. Yeah, so it's like this. You can discretize it. Okay, and once you have it discretized, you could run our algorithm from before. Okay, hopefully these layers are correct. Sometimes they aren't, but at least you get the idea. Okay, so the nice thing is that this algorithm is correct. I can take my input, chop up the edges, feed it into BFS. I feel very good about the correctness of BFS, right? All right, there's only one problem. Yeah, yeah, running time. So what's the running time of this algorithm going to look like? Yeah, it's going to be like the sum of the edge lengths or something like that, right? And why is that problematic? Yeah, so in particular, a really, really large edge weight only takes logarithmically as many bits, right? So your edge length would be 1 billion, but you only need a log 1 billion bits to write that down. So your algorithm is going to suddenly take a huge amount of time proportional to its input size. Yeah, you don't want to do 1 billion iterations just because some edge had length 1 billion. Okay, so okay, so but at some level, we can still try to simulate this algorithm, right? So if I had discretized the edges, but at some level I skipped sort of the boring points, right? In particular, imagine running this algorithm and look at the original vertices in the graph. What's the first vertex that gets labeled if I had simulated this sort of clumsy algorithm? Well, S will come first, yeah, then after S. Yeah, but which one? Among only the original vertices in red. So this one here, right? This one will come first, it'll get labeled 3, right? And then afterwards, right? So we can still make an algorithm that's sort of processing and trying to skip sort of the silly parts, right? Okay, so we could do something like this, right? We could still do something like layers, but it's sort of a little more clever now. We're still figuring out what's the next frontier, next frontier, next frontier. Okay, good. What's the point of this? Okay, so that's Dijkstra's algorithm at some level, right? It's just like breadth first search, but you're kind of skipping those auxiliary vertices. You just find the next vertex that gets labeled, next vertex that gets labeled, next vertex that gets labeled. We reverse engineer what BFS would do. So the first iter, well, we first label S as 0. That's not too interesting. But when you're trying to find the next vertex, that's going to be the closest one to S by distance. This is only for non-negative weights. Yeah. And then from there, you're trying to figure out what's the next one BFS would have labeled, skipping all of the auxiliary vertices, right? And so you have like, so how do we write it here? So out of all the vertices I've labeled with some distance, plus an edge leaving it, that gives some like tentative distance. Let's get the minimum one, minimum one, minimum one. Just simulating breadth first search. Okay. All right. So let's try to prove this is correct a little more formally, especially if the weights aren't integer and stuff like that. Yeah. So I think at some level, maybe the point of interest here is the following. So with breadth first search, it was kind of clear that we could do induction on the layers, right? That felt very natural, just coming from the algorithm. 1, 2, 3. It seems like a very natural thing. But here's a little bit more awkward. Yeah. I want to probably do something like induction, because that's a nice way to prove things. But I need something to do induction on. I need to be counting something or something, right? We don't have these layers like we had before that were quite so obvious. So what, how can we set up the proof maybe? Yeah. Yeah. Okay. So I can induct on a number of nodes that I've already kind of know it's correct for those. I agree. But now I kind of want to, so, and I just want to take that and clean it up a little bit. Yeah. Induction. So that would be like, oh, if this algorithm works for n vertices, or if it, I want to know if it works on n vertices, assuming it works on everything less than n. Could you do that? Well, how would you do that? Try to imagine. Starting node. Okay. So that would be okay. So just to repeat, I think the idea was like you have some starting vertex s, but you know how to solve problems with n minus one or fewer vertices. So let me try removing it, and then let me run Dijkstra's algorithm from everybody else to get distance from everybody to everybody. Then put s back in, and then check s goes to here, and then a distance to everyone else. S goes to here, distance to everyone. So that would be a working correct algorithm. Uh, but it's not the algorithm we're trying to prove is correct. But it would use induction to give a correct algorithm. I'm a little concerned about the running time. I think it's going to be exponential. But yeah, so that's a slightly different question. The question is, how do we prove our algorithm, which is sort of intuitive? I think we all believe it works. It should work because it's basically BFS. But I want to just figure out how to formalize it. So the idea was something like the vertices we already know is correct, which I think is kind of a good idea, but I want to clean it up a little bit because it feels a little circular. Okay, just to repeat verbatim, so say that again. Okay, so you're saying the distances are stored, the distance labels are storing distances from V. So if I add a new node, it's going to be correct. Okay, well, so if you wrote, if that's what we wrote down verbatim, it's a little ambiguous. Like, what if I added a node that was very close to S? I don't think that's what you mean by added a node, right? So we want to clear up that language a little bit, right? So I think we all have good ideas. We're just trying to figure out how to clean it up. Yeah. Okay. So we'll try to do induction on distance. Oh, if I figure out everything in distance one, two, three. The only thing that's a little weird is that there's sort of like infinitely many distances. But that is, I mean, that's how we're thinking of it, right? We're sweeping from S from the shortest distance to the longest. I mean, even if it was like fractional edge weights, I could have discretized the edges to be even smaller or something, right? So that's certainly intuitive. The only thing is, at least clean induction arguments, you want something nice and clean you can count instead of like a continuous spectrum. Yeah. Yeah, I think this is similar to the idea of known knowns and unknown vertices. I think that's right, but it feels a little weird because okay, here's an alternative, which I think is somewhat similar but subtly different. So so the algorithm is going to label the vertices in some order. Yeah? Because that'll give me some ordering I can work with. Okay? I'm just trying to set up an induction argument at the moment. I think we're all kind of circling around the right thing, and I'm just figuring out how to get it down clean. This might not be the only way. Okay? And now I want to show that for every I, okay, one, that VI is the ith closest vertex to S, right? And I want to show that I get the right distance for VI. Yeah? And I want to stress this point that we're proving both of those things. And you can kind of imagine why that might be useful, right? It feels like to figure out the 10th closest, you need to know the ninth closest. And to get the right distance label, you need to get the ninth, 8th, 7th distance labels, right? It feels like you need both of those things. The algorithm won't work even if it's some miraculously getting right distances if it's not the right order or something like this, right? So I think this is the most important thing, just getting the setup correct. This might not be the only setup, but I think it's a relatively clean, clear setup. And hopefully now it'll be somewhat straightforward. Okay. All right. So Okay, I want to prove this. Actually, it's already kind of set up, but what would be like the base case? We start with 1, right? I mean, we want to prove this for all I. You might as well go in increasing order. Feels natural, right? The base case, I is equal to 1. What's there to say? Go ahead and say it. Yeah, it's the source vertex, right? The distance is 0. You can't do less than 0, so you know it's got to be the closest. I'm assuming non-negative edge length. Okay, good. All right. What about the case when I is bigger than 1? What can we say? Looking at the 10th vertex that the algorithm labels, right? And now I want to argue it really is the 10th closest vertex and that the algorithm will give it the right distance. Yeah. Yeah, it has to come from one of the preceding 9, whatever the, let's see, what the, not sure what I wrote. Did I write anything? Oh, okay, yeah, yeah. Yes, I think, let me put it this way. I guess it's sort of, it's okay. Okay, so in truth, I want the ith closest vertex, right? That's reality. I mean, that's the actual truth of the matter, regardless of what my algorithm does. And it's always going to have to be the closest, or it's going to be some path that goes through some vertex that's closer, right? And the distance to it is going to be like, well, that previous vertex plus the edge length. So we can characterize the ith closest vertex as like the head. Okay. Overall, choosing one of the earlier vertices, one of the first 9, taking the distance to that vertex plus adding an edge, where do you land? Right? And whatever is the best one will give you the 10th vertex. And our algorithm is doing the same thing, but with respect to the distance labels. Right? It's looking at the first 9 distance labels, adding an edge length, seeing where you end up, and choosing the best one. And then by induction for those first 9 vertices, you get the same distance label as a true distance. Yeah, so by induction A, I think there's 2 things to point out. One is that you're already agreeing on the 9 closest vertices. And the second by induction is that you're getting the right distance labels for the first 9 vertices. And that sets you up to get the 10th one. Okay. All right, so nothing special. I think everyone understood this implicitly, and it's just one way to articulate it. Any questions? Wait, this might have gone way too fast. Uh, yeah, okay, these are equal by induction. Okay. All right. Any questions? Okay, so, okay, this relatively, we're going to make this faster in a moment, as you may have already heard it before. But let's go through the running time of this algorithm. Okay. So how many iterations of this outer loop do we do? This outer loop labeled A until all, or two, all until all vertices are assigned a distance. Number of vertices. Okay. And then if I'm not optimizing anything, how long would this inner loop take? M? Yeah, I mean, maybe you loop through all the edges or something. At least that's conservative. Put that together, you get M times N. Yeah. Okay, good. Okay. So simple enough, relatively intuitive algorithm. It's like breadth first search, but you're kind of skipping some stuff. Okay, good. All right. So now we're going to try to make this algorithm a little bit faster. Okay. So, all right. So we're always looking for this like next minimum tentative distance. Okay. So whenever I have some distance to one of the first 9 vertices plus the edge length, that'll give me a tentative distance to some yet unlabeled vertex, right? I'll call that a tentative distance. And then when I add that 10th vertex, right, then I'm going to need some tentative distances next iteration. But at some level, like I've already computed stuff related to the first 9 vertices, and I should only have to update for the edges leaving the 10th vertex, right? So even if you just optimize for that and you just like save it in a table, that'll reduce that inner loop from OM to like ON or something, because each vertex. Okay, good. Now, so we want to key in on the fact that each iteration is updating some of the tentative labels, but not all of them. Okay, and try to reuse our computation from before. Okay, so, okay. All right, suppose we had a data structure then. Uh, Presumably you've been exposed to some of this before in your data structures class. Okay, that at some level is a heap. Okay, so you have some keys with certain priorities, some values, and you can insert an element with some priority. You can remove the minimum priority element, or you can actually take an element that's inside your heap and decrease the priority more. All right. Any ideas for how to leverage this in our sort of naive Dijkstra's algorithm? I'll just leave it like that. Yeah. Okay. I think you're absolutely, we're in agreement. Let me change the wording just a little bit though. I want to think of keys and priorities. Keys are like the name of the thing, and priority is like the weight or the thing. So what would be the key? Some vertex, and then what would be the priority? Yeah, there's like tentative distance thing. So that's how we're going to try to use it. Yeah, we are going to use a heap. Okay. And, you can be lazy. I mean, and just initially, I'll just make everyone's tentative distance infinity, except for S, which will have tentative distance 0, because I don't know how to get to everyone else first. And I assume I can handle infinity. Okay, I'll just dump everything in so I don't have to reinsert it later. Yeah, yeah. I just kind of like change the rules a little bit and do whatever's easiest to write down so that it's easiest to communicate. Okay. But the point is the heap is getting the tentative distances so far. So each iteration, I just find the next closest one. That's the minimum tentative distance. Say, oh, I marked that as final. And then for that vertex, I need to explore its neighbors, right? Because the ones it can get to in one hop might have improved tentative distance. Okay, so I loop through the neighbors and update some values. Okay, just accelerating the same algorithm from before, reusing computation and such. Okay, no big deal. All right, how long does this take? If I'm just using a log n time heap, every operation takes log n time. All right, m log n, but why? Well, each vertex goes inside the heap. You put each vertex inside the heap. So where does m log n come from? Okay, so how many iterations here? All right, n iterations. N n. Okay, so we always do n is equal to number of vertices, m is equal to number of edges. And then like don't ask me why we chose the only letters in the alphabet that look and sound the same, except we also did it for I and J, so it's like a tradition. Okay. All right, so there's three loops of the Q one, right? Because each time you're pulling out n loops, sorry, for loop in line three, there's n iterations because each time you're pulling out a vertex. That's okay, so that's n. Okay. This will take a log n time, I guess, to remove min if we just assume log n for everything. Okay. This is what? Constant time. And then for each outgoing edge, how long does this take? Yeah, it could be m, or we can write it as the out degree of v, number of edges that are leaving it. And we'll see why that's helpful in a moment. This operation on the inside is going to be decreasing the priority of a key. Let's say that takes log n time. Okay. So there's a couple ways to look at this. One, naively, if I focused in on this m, it looks like m n log n or something, right? Because I have n on the outer loop, m on the inner, and log n for each. But the suggestion was m log n, so why? Yeah, so another running time. So you have one n log n from this step here, plus you're summing up all the vertices, degree of v, and then you decrease a priority. So we're just kind of like pulling the inner loop out when we count. We're in particularly looking at this is the bottleneck. Okay? It's sort of, it looks like it's in a nested loop, or we can just sum up the total sizes of that inner loop. Degree v plus degree v plus degree v. Yeah. How are you able to decrease the priority of a key in a heap? If you're doing a min heap, doesn't this just bubble up? Oh, where it is in the heap in the first place? Okay, so then you can start maintaining like a table and reverse links. You just keep up. So if we just keep for a table that says for each vertex where it is in the heap, and whenever it moves in a heap, I update the table, right? It's just reverse pointers. Yeah, it's a little clumsy, but that's okay, right? Yeah. You can also insert a new element. Um, we could also insert something new for every edge. The outer loop will have length m, which here won't be an issue. That's true. That's true. Okay, so let me just make this one last point in case it wasn't clear. The sum of these degrees is m, and that's where we get m log n. Okay. Yeah. Yeah. It's m plus n times log m plus n times log n. Yeah. I mean, properly, I probably should write that. Yeah. Yeah. In most cases, like for example, you could start at S, run DFS or BFS, and just get the vertices S can reach, and just focus on that part of the graph. In that part of the graph, m will be at least like n minus one because it's connected, or it can reach everyone, right? So there's at least a tree in there rooted from. Okay. Um. Yes. Good. All right. So we're gonna do just a little bit better. Okay. Using this very, very nice eccentric data structure, which maybe we'll come back to at the end of this semester. It's called a Fibonacci heap. Okay, it's a specialized priority heap. Let's read it off. Okay, so first of all, it's going to give you an amortized running time. Okay, so it's not really saying that each operation takes this time. It's sort of saying in the aggregate, it's going to be as if each operation took this time. And we'll talk amortized analysis like more slowly towards the ends of the class. For now, we just need to get used to it for this one moment. So, say you do a bunch of insertions, you do a bunch of decrease keys, and you do a bunch of remove mins. And you say, what's the total running time? It's going to be as if each insertion took constant time, each decrease key took constant time, and in each deletion or remove min took log n time. Okay, so this is called amortized time. It's not true that each operation will actually take log n or constant time, because inside the data structure, it's going to occasionally rebuild. It's like you're programming in Python, occasionally it's a garbage collection or something. So there are moments where the algorithm is going to seem really slow, but on average, it's going to be just fine, because it's sort of doing a lot of work that can be charged off to before. That's the same kind of logic here. Again, we won't go into in detail now. Okay, but you can just think of each remove min as taking log n. It doesn't really mean each operation takes log n, but if you did 10 of them, it would take 10 log n time in hindsight. Okay, just the work is unevenly divided. Okay. All right. So let's plug that into our algorithm. And I guess I left some boxes for us to fill in. So we already did, right? Okay, so how many iterations? At the top in 3. This we just did it. And iterations. Okay. In 3a, when I remove the vertex's minimum tentative distance, how long does that take? Yeah, it takes log n time. Okay. And then, right. So let's go to 3c1. So when I'm setting this distance here, how long does that take? Yeah. Constant. So the amount of time I spend per edge is now the constant. Or yeah. Right? Good. So if you put all that together, what running time do we get? Just someone say slowly and loudly. N log n. Uh, okay, that accounts for these two plus m. Okay. We still do look at all the edges, right? So, but we remove the log n off of m. Sometimes m is much bigger than n. Yeah. Yeah. If you want to do decrease and increase, you can't get this bound anymore. Yeah. Fibonacci heaps are like super clever. I think a major open problem is trying to get it to worst case running times. Try to get actually log n worst case running time instead of log n sort of an on average, which is what amortizes. Yeah. But people have been trying for like 40 years or something. Okay. And it's also doing clever things. So I haven't looked at it in a while. But first it maintains a bunch of heaps, smaller heaps that you occasionally glue together. And you know how like a Fibonacci sequence, 1 plus 1 gives you 2, 1 plus 2 gives 3, 2 plus 3 gives 5, 3 plus 5 gives 8. So it'll do things like combining the heap of size 2 with the heap of size 3 to get a new heap of size 5 and stuff like this. That's where the name Fibonacci comes from. And I kind of forget the details, but yeah. Once when I was your age, I understood this, for a few weeks. Yeah. If you guys are excited, we can do it at you guys will have the tools to do it at the end. It would take a whole lecture kind of focusing on heaps, but yeah. Okay. But it's a pretty cool. It's one of the more celebrated data structures. So this wasn't didn't do this in data structures. Do you guys do much amortized analysis in data structures? Okay, so wee bit. Okay, so okay. Huh? Okay, okay. So we'll do it. That's actually a super useful thing because yeah, it's very practical. Yeah, sometimes rebuilding. Yeah. Okay, good. All right, good. So we finished a little faster than usual. I guess that was to be expected, but to some extent this was anticipated. So now we can do fun problems. Um, Let me introduce this one first. Okay, so before we found the shortest, the distance from S to T or something, right? And that was just the shortest way to get from S to T. Now suppose I said that, and that was just this 447 or something we decided. That was 15, despite claims of 12 or something. Okay. All right, now suppose I told you you had to use an even number of edges. Yeah. Uh, can't you just do two deep searches and then call the function? Okay, okay. So we're okay. Well, first, does anyone figure out what the best even length is on this graph? Milk this for all it's worth. Even. You have to use an even number of edges. 3, 3, 4, 7. So that adds up to 17. Anyone beat 17? Okay. But it's trickier, right? It clearly throws a wrench into the problem. That much I think we can agree. Okay. Good. Good. Now, okay. So the suggestion was, can I add all pairs of edges? Can I make an auxiliary graph that sort of has all like two steps at a time into one edge? So I'll draw some of these. Uh, so like this edge here will be 8. So I'm going to make a new graph with the same vertex set, but only the red edges that I'm drawing now, right? 3 plus 3 is 6. 3 plus 2 is 5. 4 plus 5 is 9. 4 plus 7 is 11. 4 plus 4 is 8. Uh, 3 plus 4 is 7. 3 plus 7 is 10. 2 plus 3 is 5. It's going to take a while. 8, 7, 8. Okay, imagine I did all the other red edges, right? So each red edge represents two steps in the original graph. Then we could just run Dijkstra, right? It's going to say, oh, these 5 edges got you this distance. And we know that's 10 edges in the original graph is the same distance. Okay? Now, the original graph, let's say, had m edges and n vertices. Okay? So how long would it take? First, we need to build out this graph, right? How long would it take to build out this graph? Can't you square the, yeah, you can, just squaring? Not quite, but I think that what we end up, if you just did the old fashioned, I mean, even if you think about squaring the adjacency matrix, you're just doing the loops, right? So you're just kind of for each vertex going through a loop of stuff. So we can still describe it in combinatorial terms. We won't lose too much. So combinatorially, yeah, how would you build this graph? Maybe for like each vertex, you have to choose one incoming edge and one outcoming edge. You know, we can focus on the middle vertex that we're skipping over, right? So each vertex can choose one incoming edge and one outgoing edge or something. So it'll be like the sum of degrees squared or something. So maybe that's like n cubed at worst. maybe n cubed time to build the graph. And how big is this graph? Yeah, it could have n squared edges now. Okay, so if we ran Dijkstra on this algorithm, on this graph, we now are starting to look at something like n squared plus n log n, just for the Dijkstra part, plus building the graph, which looks like n cubed. I think you might actually be able to do slightly better, but, or no. Well, maybe complete graph you're screwed. But you could get it in terms of m and maybe do better on sparse graphs. That's okay. But leave that aside. Okay, so we have some running time that's at least n squared, maybe n cubed. Yeah. Okay. Okay, so first to make it clear, we have something like an n squared or n cubed running time. Maybe you could do better than n cubed if you're clever about building the graph, but at the very least, running Dijkstra on the graph is going to cost you n squared. The question is, can we get it back to something closer to the running time of the input graph? Okay. All right. So let me, I should have copied and pasted this before. So the suggestion was, can we do something that's sort of like, instead of having an odd and, instead of having these distance labels, can I maintain like an odd label um, and an even label and stuff like that, and like try to update that. So I think we kind of have a sense what this algorithm is, but suppose I was running this algorithm and I'm updating odd and even labels. So like, which one would I do first? Like, let's just simulate the labeling part. What would be the first label? Sorry? Okay, so first I think we'd say like, oh, the even is 0 for S. Okay, then what? This one? Well, you have to be careful about which one you do first at a time, right? Because there could be times where you don't want to, it can't just be adjacent. You have to make sure you pick the closest one. Otherwise, you can get out of order if there's some, right? So, okay, so that one, and then what's the next one it would do? Or it would say this one odd, the odd one is 4, and then what? Maybe this one? And this one would be like even 5, something like this. So we just try to like keep optimizing the next best odd or even label or something like this. So I can maybe try to imagine taking, one of our pseudocode like this and basically making it like twice as big or something to account for odd or even. Yeah. And then I would kind of have to go through and redo all the proofs, even though it would seem to be kind of similar, right? I have to make a proof that's like twice as long to account for odd and even. Plus it would start getting awkward because, for I equals 1 or 2, 3, 4, is VI the third closest or is the third odd closest? Imagine trying to do a proof for this algorithm. I think we have the same idea of algorithm in mind where you have odd and even labels, you're kind of updating them next closest order. Then you have to start proving it. And you're thinking to yourself, well, it should be sort of the same proof, but now notationally it's going to be a pain because what if V2 is even? What if V2 is odd? What if V5 is even? V5 is odd. Is each vertex going to appear twice in this list, right, for odd or even? Right? If you make a new algorithm, you're going to have to prove it's correct, right? So I think this will work, but it's going to be difficult, yeah.
For each tentative distance, it's either an odd number of steps to get there or an even number. So all you do is every time you update, you store the best odd, and every time you change the tentative, then
Yeah,
you switch it.
I agree. You're going to have some pseudocode that look like our pseudocode from before, but it's going to be annotated with odd or even. And if the tentative, yeah, you're going to update some tentative even distances. You're going to update some tentative odd depending on the preceding vertex, right? But imagine the code's going to be like twice as long. It's going to take that inner loop, make it twice as big because you're going to have all this odd or even. Imagine trying to do the proof. It's going to be twice as long and maybe more messy. Because before I could say things like, oh, V2 is the second closest vertex, V3 is third closest, and that was relatively simple. Now if I need to account for odd or even, right? Second closest vertex if it's odd, but not, imagine it's getting a little messy notationally at least, right? So what's a way to simulate this algorithm? Okay. Absolutely the right idea. We're not going to do better in running time, even if I bother to prove this version. Okay. But I don't have to change our Dijkstra algorithm at all. I want to do effectively the same thing, but I want to not do anything on the homework, right? I just want to say, I'm just going to use Dijkstra. I don't have to reprove it because we already proved Dijkstra has these properties. Yeah, we have these graph algorithms. We understand their properties on certain inputs, right? Let's not reinvent things. Yeah.
So, I mean, are we the sentence solution to use Dijkstra's
Yeah, as a black box, we like to say. Can you use Dijkstra's algorithm as a black box without opening? Because I think this odd or even thing would work, but nobody wants to type that out. Yeah. Yeah. Okay, so what can I do? I can try to make two vertex sets, two copies of the same vertex set. Okay. I'll call this copy V odd. No, I'll call it V even. Okay. And I'll call this copy V odd. Okay, so inside we have lots of vertices. And it's two copies of the same vertex set. Okay. And then for each edge, so let's say that like S is this one, and I'll call this one X. Okay. And say this vertex here corresponds to X. The two copies of X, the odd copy, the even copy. And that edge had length 4. So what I'm going to do is I'm going to add an edge like that of length 4 and an edge like that of length 4. Okay. And so I'm going to build this auxiliary graph, okay, where I make an odd copy, a copy labeled odd for each vertex and a copy labeled even, or sorry, even and odd. Now I'm going to add the cross edges. So what used to be just normal edges will be crossed, okay? So what are these vertices going to do? They're going to represent a little bit of extra state. When I am on the even copy of S, that means I've taken an even number of edges so far to get to S. If I take one more, I'm going to be at the odd version of X because I've taken an odd number of edges to get to X. Yeah, this is exactly your odd and even labels, but made explicit in the graph. Right? So you had the idea, but this is presenting it differently. Okay? So I'm backpacking a little bit of state into the auxiliary graph. Okay? I build up this graph, and now I just try to find the shortest path from where to where. Or from where. Yeah. Yeah, okay, let's go over that. So in this graph, how many vertices are there? 2n vertices. And how many edges? 2m. Yeah, again, they sound the same as always. Okay? It's not any bigger. It's only twice as big. That's nothing between friends. Yeah? It's hiding in the big O. We don't even care. Right? So the graph is only twice as big. Yeah. Yeah, so where should we start our search? I still have to give it to Dijkstra, right? So Dijkstra, I give it a graph, and I give it a starting vertex. So what should a starting vertex be? S even, because it's really, I've taken 0 edges, and that's even. As soon as I take 1, that'll be odd. All right, I run it from S even, right? And I get these distances in this auxiliary graph. And then I wanted to find the shortest distance from S to T using even number of edges. So which one do I return? T, which one? There's two T's. T even. Okay. So in your solution, you just say, well, I'm going to create this auxiliary graph. You describe it explicitly. I make 2 copies. I add these edges. Maybe add a sentence, explain it intuition, because that sentence would make it very easy to understand what's going on. I give it to Dijkstra's algorithm. My graph had this many edges, this many vertices. So Dijkstra's would take this much time just plugging in. And then I return the distance to T even, right? So once we use the black box, we still have to get the solution to our original problem, where there's a slight gap here, right? Okay. But that's way better than reproving Dijkstra was odd and even labels and going through all this nonsense. Yeah. Okay. All right. Good. Any questions? I have more puzzles like this. Okay. I'm going to give you an infinite number of these graph problems with increasingly absurd stories. And if you try to reinvent Dijkstra, you will not solve it. Or even if you did, we will not be able to grade it. Yeah. Ah, good. I skipped this. So we should still prove it works, right? So here you would say what you want to do is you want to be able to map the even length paths in your input graph to paths from even to even in this auxiliary graph. So, oh, you give me an input length. If I have this graph with an even number of edges, if I have this path with an even number of edges in the input graph, look at this graph in the auxiliary graph where I go from even to odd, and I just construct that path in your auxiliary graph. Say, oh, this path has the same length. So that means that the distance here will be like greater than or equal to the distance here because that path in your input graph also exists in the auxiliary graph with the same distance. Okay, so that shows that your algorithm will return a value that's less than equal to the answer. Now you just have to go the other direction. Suppose I have a path from S even to T even in my auxiliary graph. Well, look at this graph in the original. Look at this path in the original graph, which is going from, if it's going A even, B odd, C even, D odd, it would go from A to B to C to D. And you say, oh, it's still an even number of edges. The edge lengths are the same. So you get this distance, an even path here. So that means that the number you output will be greater than equal to the answer because every path here exists here. So you just have to go back and forth. You just do the bijection. I don't see any other way to do it soundly. Usually if you get the right construction, it's relatively straightforward. You just have to map one object to the other and back. Okay, but make sure you do both directions. And it's not uncommon, first couple times you do it, to think you're doing both directions, but you just do the same direction twice, So be a little careful. But with practice, you'll get good at this. I think the hard part is finding the right tricky graph. And then the better, once you're able to solve it, you might find it a little cumbersome to do the proof, but it's still good to do the proof. If you don't solve it, you'll find it hard to do the proof, and then you'll be like, oh, I have the wrong thing. I should go back and fix it. Yeah, proving is partly to convince ourselves that it's correct. Okay. That was a good question and also, highlighted something I shouldn't have skipped. So other questions? All right. I loaded up some more. One is maybe a little easier, so we can do it quickly. Okay. So another one is, uh, suppose I wanted multiples of 5. Now what would I do? Okay, five layers of this graph or something, right? So I'll make 5 vertex sets. This is 5 vertices of the vertex set. I wish I drew that better. Okay, but then how are you going to draw the edges? So from like left to right, and then the fifth one will loop back. Yeah. So every time I walk around, that represents 5 edges. Graph is only 5 times as big. Yeah. And then similar idea. Okay, so that was obviously uh, that was just for people who didn't pay attention to the even in previous classes. Okay, how about the next one? Multiples of 2 or 3. Okay, we can make 6. Okay, so I'll call this one, so I'll call 0, 1, 2, 3, 4, 5. Okay, tell me how to draw edges. Okay, so first I'll have edges going up. Yeah, you can also run it twice. Okay, one sec. I think I have more fun ones. Okay, this is where it gets better. These were going to be, and they might still be on your homework. Um, all right, here's some fun ones. We can ignore the second part. Okay, oops. Can you get the shortest walk from S to T where the number of edges of the form 5x plus 8y for some integers x or y? Or non-negative. But you want the shortest one, right? Oh, if it's negative, yeah, well, yeah, no, I do non-negative, but it could be zero. You're gonna try to make 40 graphs? Are you sure that's correct? Because it's gonna be hard to draw. But luckily we have a doubling trick. Okay, that's 32. All right, there's 40, and I'm pretty confident about this. Isn't that almost everything? Because it's going to be like mod 40 or something, right? So like 13, are you going to check 13? You got to make sure you check 13. You're not just checking 5, 10, 15, 20. All right. So maybe I'll leave that there because it's going to be on your homework then. This will stump you. But this is a fun one, and there will be more. But you get the game, right? So think about, what these algorithms are actually doing on the graph, right? And think about how to encode the problem in the graph and things like this. Yeah, and then you're really going to see how many things you can solve with relatively simple algorithms. There's not that many different algorithms out there. Yeah, they're just different inputs. Okay, so that's the thing. All right, we'll end there. Knock yourself out over the weekend. And Peter